My name is Jeremy Nilmeyer. I'm a developer advocate for IBM. I work for a center called the Center for Open Source Data and AI Technologies, and I'll talk a little bit about our mission there. And it's an honor to be here. The last time I was here, I was still in graduate school studying biophysics. My advisor was a graduate of Columbia, and we collaborated with Columbia on a lot of research projects. So the last time I was here was back in graduate school. So it's really great to be back, and it's a beautiful campus. So just a little bit about me. I started out, as I mentioned, not in the area of computer science. I actually started out as a chemical engineer. Eventually got into a biophysics program, did sort of computational biophysics, so I learned how to program solving biochemistry problems, and got more interested in the computing side of it than the biochemistry side of it, and eventually sort of reshaped my education around that. Ended up landing at Lawrence Livermore Labs, where they have the great big supercomputers, and started to do high performance computing there, and then did some programming with some GPU accelerated molecular dynamics code at Stanford. But eventually, with all of that sort of the high performance computing version of big data training, I kind of retooled it using in a boot camp called the Insight Data Science program, and it's a wonderful program. There are also many others that you can get into to kind of specialize your training for the private sector. And this is like about a 6-week boot camp, and then you get a back in California, you could do a tour of like the Silicon Valley companies as part of the interview process. So it's a really great journey. But the idea behind all that is that we don't all come with the full tool kit to solve all the problems that you may encounter, but we need to it's nice to have a place to start, have an idea of if I just had to pick a few things to learn to call myself a data scientist, what would they be? And so O'Reilly contacted me, and we worked out this book here. It's just a little less than 100-page text. It's freely downloadable if you go here and download it, and it just kind of walks you through how to get started on some of the frameworks that we think are some of the just the basic ones to get you up and running. And all the notebooks are in this GitHub here. And then finally, I'll walk you through. We have a what's called a free hosted notebook environment. Just a show of hands, when I say Jupyter Notebooks, how many people are familiar with those? Okay, great. And so we have a hosted notebook environment that provides all kinds of nice runtimes, GPU accelerated runtimes, Spark runtimes, and things like that. So if you go there and sign up there, then I can tell them that you guys stumbled across it based on this conference. So I'll get to come back. This is one of my favorite conferences to come to. So I'd love to be able to come back. And then we also have a lot of TensorFlow. All the examples, I'm going to walk through lots of notebook examples today, and these are all just in a box folder that you can download using that link right there. So if you want to follow along, please feel free. So the idea is, if you want to go from like 0 to hero here, what would it take to learn? And we definitely, strongly advocate for the use of the notebook environment. And so, for a while there were many notebook environments that were out there. Zeppelin was a prominent contender. But Jupyter sort of emerged as the most robust notebook, and the developer ecosystem is just enormous. So we sort of advocate for that. Within the notebook, you can run virtually any kernel you like. You can run Scala, you can run Tori, you can run Python clearly, and so it's worth kind of working out all the details of getting all that to work. If you're going to do distributed machine learning, we think Apache Spark is the one to learn, and that'll give you access to all kinds of libraries that would otherwise require separate installations. And so if you can sort of see pretty much any kind of data big data application from within an Apache Spark context. So it's definitely worth learning. And then, Apache Spark will start to run aground as you start to require GPU resources because it's mostly a Java-based environment. So there's lots and lots of GPU accelerated deep learning environments, but TensorFlow tends to be the one that people really favor. Again, the developer ecosystem is enormous right now. It's got something like 41 million downloads at this point, one of the largest projects ever to be available in the open community. So it's really great. So again, just to stump a little bit for this notebook thing, it's not just the developers that get to use these things, it's everybody in the organization. And it really has been adopted company-wide for lots of big companies like Bloomberg, Netflix. There's a bunch of other companies that have really just kind of taken it across the board, and this means that everybody from technical leadership to legal teams to management, everybody is sort of communicating through these notebook environments. So it's kind of fun, as a data scientist to kind of fiddle with this stuff and get to learn these things, but it's also now a pretty widely accepted medium of communication. It can be included as an appendix if in a publication, and you can always run live code in it, so it's really great. And just to kind of remind of ourselves of what IBM has done in terms of its history with open source. And this really started with the Linux project. This was back when there were a whole slew of operating systems, lots of proprietary Unix environments. MS-DOS was coming out. And Linus Torvald said, hey, I kind of want to do this open source kernel thing. Maybe we can kind of have this, organically grown Linux environment where people contribute as needed to make the kernel robust. And they said, okay, IBM. So IBM got involved with this and said, okay, we'll create something called the Linux Technology Center. And the mission of any of these technology centers that IBM creates is to promote the use of an open source project within the IBM community and then also across all the communities that are involved, so we can have shared interests in these. And so we were one of the original founders of the Apache Foundation, the Linux Foundation. We also created something called the Java Technology Center. The Java Technology Center resulted in the development of an IDE called the Eclipse project, which was about a $50 million investment. And they released that into the open community and made it freely available. And then since then, we've been pretty much involved in all of the open source projects that have really come into being. Try to get in on the ground floor and get involved in the open governance side of it so that we can influence the project. And then so Apache Spark, we were involved with it when it was still a university project, and some of the other ones there. So we're also really involved in the idea of an open standard. So we have this predictive model markup language, the open neural network exchange format. We're also not only involved in data formats, but actual data provenance. So we have something called the data asset exchange, where we make sure that the data that's being released has correct lineage and is usable. If you wanted to use it to train models that are going to be used for commercial applications, is that data okay to use, and things like that. So the idea is, a rising tide lifts all boats, and just to remind us of what the power of these open source projects are. The Linux project resulted in the founding of Red Hat. We acquired Red Hat for $34 billion, and that company had absolutely no IP. So open source is really a viable way of building the code, and probably the best way to develop these large projects. So the center that I belong to is the Center for Open Source Data and AI Technologies. And so our job is to advocate for AI frameworks, which includes all of the deep learning frameworks, big data frameworks, which is things like Apache Spark, and various open source projects that kind of belong to that ecosystem. I wanted to just point you to how many people are familiar with deep learning applications in general, like what deep learning is capable of. How many people are sort of new to deep learning? And okay, so we've got a little of both. This, if you are relatively new to deep learning, maybe even know what how the fundamentals look, and you want to see what the applications look like, this is a great little sampler of Docker images that you can just download and then just run, and then they'll present a REST endpoint, and then you could submit images and it'll do object detection, for example. So it's very easy. So within less than a minute, you can get any of these up and running, and you can see what they can do. And give yourself an afternoon, and you can really have a good survey of the field and the applications that are available. All free, all open source. Most of it's built on TensorFlow. There are other ones that are built on Caffe and PyTorch and things like that. So this is actually a framework agnostic exchange. But I do, in general, like to at least touch on the very, very basics of neural networks, just so we have a common language, and then we'll get into some examples and we can talk a little bit about it. But just the basic idea of a neural network is you've got a neuron here and so really all the neuron is it takes an input and transforms it into an output. And so it's a function, and that function takes this z value, which is the sum of features times weights plus a bias. So the features are the inputs, the weights are these parameters that we have to discover through numerical optimization, and the bias is also a parameter. And so that number gets fed into this activation function. This activation function takes on various forms, and one of the most common forms is a logistic form. The idea is that it's in a continuous approximation to a step function, because a neuron is supposed to be either on or off. At some point it hits a threshold and it fires. And so we try to replicate that effect with this logistic function that goes from 0 to 1. It has this sort of saturation feature. In practice, that does not always result in the best numerical properties when you're trying to optimize the function. So we usually do something called the rectified linear unit, which is this function down here. And this function here has slightly better gradient properties, because then it doesn't saturate at one end, which you have this problem called the gradient vanishing problem, which creates numerical difficulties. So you either have something that's like a logistic function, maybe towards the output, and then all of the internal layers tend to have these rectified linear units for the activation functions. And so these neurons are almost always arranged in this dense layer arrangement. They don't have to be, but it turns out that this is sort of the common language that people use when they describe this. And so really what they do is you just have one layer of neurons, and then you have another layer of neurons, and then layer 1 is only connected to layer 2. It's not connected to any other layers in front of it or behind it. In principle it could be, and actually, as we'll see in even the Keras API supports really complex topologies. But in general, it's much easier to think of these things as just a collection of layers that are connected by these dense weights. And so if you think of any kind of supervised learning algorithm, is that you have a set of features which is called X, and then you have an output which is called Y. What you do when you train a supervised learning algorithm is you feed it a label, which is the Y value, then you feed it the feature, which is the X value or the X vector. And you do that lots and lots of times, and then you discover the parameters for that particular function. Well, that's all that's happening here. This is a supervised learning algorithm. You're feeding it a bunch of features, and then you're getting a bunch of outputs, and then you're training based on that. In this case, the output is a category. So the category can be one of 10 possible categories, because this turns out to be the MNIST data set, which just goes from 0 to 9. And the input is this unwrapped image. So you just take the image and you unwrap it, and now it's a feature vector, and then you feed that into the input layer. So the input layer is the one that takes in the features. the output layer is the result. So if this were just a simple function, it would just have the input layer and the output layer. But the fact that it has these other layers in the middle, it adds these hidden layers, which gives the network depth. The depth is where we get the deep learning part. So all of these internal layers is really what gives, improves the performance of these predictions in ways that we just can't see using these, just the simple input-output. So the real advance, the reason why we call it deep learning is the real advance was we developed the numerical algorithms and all of the approaches, and the hardware started to catch up that allowed us to compute these networks that had these internal layers. For the longest time, we really couldn't get them those numbers to converge based on the way we were feeding. And a lot of it was, we weren't using backpropagation properly. We weren't using the right activation functions, and then the hardware just wasn't there at the time. And so now all that seems to be in place, and now it seems to be, really the sky seems to be the limit. The only real limitation is now computing capacity. And it's, there's been openly released trained models that have 1.5 billion parameters for these neural networks. So these, it's just really, it's really mind-boggling how far it's come in terms of the robustness. And so last time I was at Data Council in San Francisco, we were working on this recurrent neural network model, so I just thought I'd throw it in there. Just to kind of remind you that these neurons can be that simple activation form, but they can also have a slightly more complex form. So this is what's called an LSTM unit. And this is basically a neuron that has lots of internal parameters that allow you to call it multiple times so that you have what's called a persistent state for each neuron. And that allows you to do things like time series modeling and other things. So basically you take this neural net, you take one of these neurons and you just call it multiple times. Every time you call it, it will emit a slightly different state. And so this allows you to do things like text processing and voice to text kind of things, and other sort of time series modeling kinds of things. Just thought I'd include it because it's actually a pretty fun project, and then you can do things like these encoder-decoder models where you can model multivariate time series. This one can be constructed in Keras, so it's completely accessible. But I wanted to jump in and sort of talk about what how many people are familiar with the TensorFlow project? Okay, great. Okay, so it's it's a simple Python API for running GPU accelerated tensor calculations, and really it was originally written just to be a Python API in sort of the same way the MATLAB was originally written to be an API to the LAPACK library. This was written to be kind of an API to the GPU accelerated calculations, and then they wanted to have tensor capabilities because they wanted to have more than just two-dimensional. So NumPy arrays are two-dimensional, and then tensors are an arbitrary number of dimensions, and then they can run on GPUs. That was the basic idea, is just to get these calculations to run on the GPU. So you can solve partial differential equations, you can do all kinds of fancy stuff if you get down to the TensorFlow API. But in general, the Keras API is what's preferred. Keras is actually not. It's just a specification. It's just a way of defining these neural networks. So they created this in Python so that you could write neural networks. And now the new version of TensorFlow has much tighter integration with Keras, and you very rarely need to use the actual TensorFlow, lower level TensorFlow operations. It does distributed calculations, which means you can distribute your calculation over one CPU, multiple GPUs, multiple CPUs with multiple GPUs, and all of that kind of combination. I don't think that it does like node-to-node communication. This is like ideally all on one chip. But there are libraries that allow for MPI communication. I can't remember, Horovod, I think it was an Uber project or something along those lines that allows for the really scalable deep learning compute. But it also has lots and lots of edge computing capabilities. So I do have some examples. I do have lots of examples, so if you guys want to usher me to one example or the other, make sure you raise your hand and let me know what's going on. so we've got an in-browser JavaScript API called tensorflow.js, which allows you to run models, allows you to train models, and it runs on all kinds of anything that supports JavaScript. And it's really great because you don't have to deal with any kind of installation issues. You can do mobile deployment with TensorFlow Lite, and then you can also, there's another even lighter weight version of TensorFlow Lite called TensorFlow Micro, which will allow you to deploy on these things called DSPs with models that have, kilobyte footprints. You can deploy Raspberry Pi, and we actually have spent a little bit of time doing the Raspberry Pi work. You can do pip3 installation. You can do the full installation and run it. You can also run TensorFlow Lite on Raspberry Pi and get better performance. But if you want to do kind of development prototyping, you can deploy the full TensorFlow version on Raspberry Pi. We also have this. How many people are familiar with the Node-RED project? Has anybody ever heard of that? Okay. Node-RED is a visual interface to Node.js, and it's really cool. We have people that advocate for this, and it's completely open source, and you can run Node-RED on Raspberry Pi, and then it's like drag and drop stuff where you can get all of your Node.js type applications running, and then you can also run TensorFlow from within that. You can run TensorFlow Lite and other things. So anyway, so TensorFlow 2.0 is the new standard. We've been really trying to get people to adopt this back when it was in alpha, because it has lots of API breaking changes, and it had the potential to have that Python 2 to Python 3 kind of vibe. And so we really wanted to say, hey, if you're going to start writing this stuff, write it in TensorFlow 2.0. It's really, this will be the stable API for moving forward. And the other thing that's really great about this is it just has, running, TensorFlow 2.0 out of the box on whatever, regardless of hardware configuration, you get a 2 to 3x bump in efficiency. So it's, they did lots and lots of work to make this a really high performance, and they've added profiling tools and some other things. But some of the sort of bigger ones is they have this thing called tf.data, which is this API for easy input management. Again, you get performance increases if you use this API. Now you call Keras through tf.keras, and it's got a lot tighter integration. TensorFlow Hub is now sort of up and running and very robust now. You can do things like transfer learning as well as pre-trained models. One of the big ones is eager execution. How many people are familiar with the 1.x API? Okay, so sometimes lazy evaluation is kind of hard to get your head around, especially when you're running stuff in Python and you expect to see results right away. But now it supports eager execution, so the development cycle for the debug cycle is usually a little quicker for exploratory work. It has a much better distributed strategy built into it now, and it has a few standardizations, which are, there are other standard models out there like the Onyx file format and other formats for neural networks. TensorFlow's standard model is going to be this saved model, and this saved model now allows you to export it all across, back and forth to the JavaScript version, back and forth to TensorFlow Lite. So within the TensorFlow Lite ecosystem, it gives you lots and lots of options. And you can export to saved model. They've also released a fairness library, which I haven't played with too much, but it allows you to deal with things like bias in your data sets and things like that in a systematic way, which we're really excited about. There's this thing called the Linux Foundation for Fairness in AI, and there are lots of open source libraries that are supported based on that, and this looks like a great candidate for that. It also had, so now you can launch TensorBoard. I'll do a TensorBoard example where you can see that TensorBoard is running, can be run in the notebooks. You can do tracing, you can do profiling, you can figure out what kind, where your code is running, and you can do all that from within your notebook. And then lots and lots of really cool edge and IoT computing applications coming out. So the JavaScript stuff is great. TensorFlow Lite is getting much, much better. There's lots of tight couple. Google and ARM are working very closely together to get lots of these TensorFlow Lite applications working on their chips. And then we have the micro, which is the really, really lightweight TensorFlow footprint. Here's the link to the notebooks that I'll be kind of walking through. How are we doing for time? I'm going to jump into some examples here, and the first one I wanted to do is just show you what the hosted environment looks like, because if you've never, I mean, it's a great experience to get to do install all the CUDA libraries and get all this working on hardware from scratch, but we have a hosted environment that allows you to do that. And this hosted environment so this is basically a Jupyter notebook that is hosted through our cloud service, and you can run Python code and a bunch of other kernels. But what's nice about it is you can pick your environment pretty transparently. So you just do a drop down, and then we've got a GPU v100 that's available here. You've got Spark environments. You've got all these other ones. So doing some quick GPU calculations, this is a pretty handy way to do it. And then you just a little bit of boilerplate to get the code running, and then you can see that we're running TensorFlow 2, and where's it's got the NVIDIA SMI that you can run to make sure it's actually running on a GPU, and then also you can check to see that the device is hooked up. So right now, you still kind of have to do a little bit of manual work to get this hooked up properly, because we're providing the 1.x GPU environment sort of out of the box, but you got to do a little bit of wrangling because this has only been released for, I don't know, a month, less than a month. But it's pretty straightforward to get it up and running. So if you're interested, let me know, and I'll be happy to show you how to do that. I just want to walk you through the overview of some of the changes. So let's go back. Let's go to the top here, and just a quick overview. So you do pip installed TensorFlow 2.0. So this is the layers library that allows you to create this neural network sequentially. So we start out with the entry point with the first layer, which is the dense layer. Add another layer right next to that, and then finally add the output layer, which has got 10 categories. And you know it's a categorical output because they like to use this thing called the softmax, which sort of preferentially it returns a normalized vector that kind of preferentially selects one category and doesn't give you a broad distribution of categories. So you can configure the layers, and then this is another way of constructing the neural network. And finally, you can do train and evaluate. So once you create these models, the next thing you're going to do is you're going to compile the models with Azure Optimizer. So this is the Atom Optimizer, sort of the stochastic gradient-like optimizer. And since this is a categorical one, you're going to create a loss function called categorical cross entropy. That tends to favor your categorical ones. There's another one. If you're doing a regression, it's the mean squared error, or I can't remember, mean accumulated error, I can't remember which one it is. and then the metrics. The metrics here that you want to track are accuracy, and those metrics will allow you that you can trace during the optimization procedure, and then you can also look at it using TensorBoard. Then you can go ahead and compile it, and then you have this model summary, which gives you basically tells you what you created. You created these dense layers and the total number of parameters. And we have to skip some of this. Some of this stuff doesn't quite work. We can run a training model here. Let me do another fit. So this is the datasets API that I was telling you about. This one's just a little bit more efficient. Again, I'm presenting this. There's a lot of boilerplate, but this boilerplate's pretty easy to transfer into your own workflow, so I'm going to provide it for you. So the data set here is now you create the batch size as part of the definition of the data set, and then you just still pick your epochs as part of the fitting process. But this, in general, will run much faster. Let's see, maybe we might even be able to take a look at, let's see, 6 milliseconds per step versus, maybe it's not comparable. Predict. Okay, so these are the advanced models that I was talking about. So now you can use the Keras API to kind of pull out bits and pieces of your network and sort of use them. And so you can create this dense layer, and now this dense layer can actually be used in multiple networks. So you just have this other dense layer as a function of the input layer, so then you can, this is something like transfer learning where you can kind of pull out chunks of neural networks and put them around. So you can do this with the Keras, and I'm not sure you could do this with Keras before, but the integration is much tighter now. So you really, even for the fancy stuff, you really don't need to get go beyond the Keras API. And they do recommend using Keras for the most part. There is this, and there's kind of mixed reviews on whether this is on best practices for this. There are folks that really are into creating a model as a class. For whatever reason, if it integrates better into their code, or if they just like the idea of it. I've heard recommendations that say maybe stick with the Keras API if you can, but you can write a class directly, and you can access to kind of lower level things, even more low level than something like this, and you can save the class. So you can, once you create the model as a class, you can save it and persist the model and the topology that's generated by that class and recover the topology. So it's an interesting addition. And then we can do custom layers. So the other thing, and I can't remember if this was in part of 1.x or not, but they have a thing called a callback. And the most common thing that a callback is something that really is a kind of a reporter that is given during the optimization procedure. And this callback here is really, the one that you see most is the early stopping one. So basically, it just prevents from overtraining. So you know that in general these optimization functions start out, the loss function starts out very large and then drops very rapidly, and then it kind of flattens out. And then so there's a kind of you don't get much bang for your buck at some point for running excessive optimizations, and GPU cycles can add up. So you want to have an early stopping monitor, and so that's what this callback allows you to do. So it's an important feature to be able to have access to. Now, saving and restoring is there's a whole variety of ways to do that, and really, we just want to make sure that we point you to these examples of how they can be done. You can save the weights, you can load the weights, you can also you can do it in JSON format, you can do it you can import it, you can export it, you can persist it from the JSON string, create a YAML string, and create the fresh model for the model. Now you can, so there's the idea of you got the configuration and then you've got the weights. The configuration is something that can be loaded and then you can just update the weights and just reload the weights, or you can save the entire model. We used to call it a frozen graph. You can do that as an H5 format, or another format that's also commonly used is the protobuf format, where it's kind of all compressed into one. So all of that is available, and then this is the eager execution that we discussed, and then this is what I think that the way that they wrote the distribution strategies for multiple GPUs is very very elegant and easy to implement. So this really is what it would look like before, if you didn't have it distributed, and now as you do is just put this with strategy.scope. You create this strategy, and then you've got mirrored strategy, and then you got this, if you have multiple CPUs, it's called multi-worker mirrored strategy, and it's pretty straightforward to generalize it to multiple GPUs. So, and then you can just do the same, and then the rest of your code looks pretty much the same. So that's that's kind of the, that really covers a lot of the, the syntax kind of things that you're going to see in the TensorFlow 2.0 API, all the kind of functionality. So how are we doing on time? I can jump into, a few more minutes? Okay. So I'm thinking I can, maybe I'll show you very quickly. There are some text processing examples here that I'd be happy to show you. I can show you the MNIST data set. I've got the MNIST data set. I've got a TensorBoard example, and then I've got a JavaScript example as well as a iPhone example. So as we kind of move into questions, just somebody raise their hand and say, I want to see that example or something like that, and we'll just, whoever is more interested, I can, go ahead and jump into there. I think we have until, what, 2:45-ish, so yeah, just feel free to kind of, let me know what you guys are interested in. So I just show you very briefly what the basic classification algorithm. How many people are familiar with the fashion MNIST data set? Okay, all right. Okay, so this is just, this is basically the same thing as the MNIST data set, which was the postal employees number, handwritten number data set. And this one here is just the same thing, it's just now it's closed instead of numbers. And so it has 10 categories, these are the categories here. And this is a really nice example because it's a canonical supervised learning algorithm, and it really shows you how to get to all of the pieces of all of the bits of data that are floating around in this. And you just create these, and then now it has a shape for the images. The number of labels is, the number of training labels is here. And so you've got labels and images. The shape of the images is a 28 by 28. Each one is a 28 by 28 pixel image, and then you can pre-process the data. This is what the image looks like. Do some normalization for the images, and then you can generate a set of figures for that, just to show you what they look like. Create your layer, and you're going to flatten your input vector. It's a 28 by 28 image, and then it's going to be, what, 784 or 764, I can remember. That's going to be the vector that goes in to, and then you begin your training based on that. The output is going to be, so the inner layer is going to have the ReLU, or the input layer is going to have the ReLU function, and the output layer is going to have the softmax function. And then you can compile it, fit it, and evaluate the accuracy. And that just shows you how to get to, where the test labels are, the predictions are. This is some plotting, and this is just one of the predictions. So it has a 94% prediction that it's an ankle boot, and then it's the distribution of the output. So this histogram here is the output layer values. You can see here that it thinks it's a sneaker, but it also kind of thinks, I think it's a sandal. So you start to see some of these more ambiguous And then now you can see what the prediction is, and then you can see the distribution of the neuron layers. So this is probably one of my favorite examples because it allows you to get into the guts of it with simple matplotlib plotting. You don't have to do anything really fancy, and you can see how you can get a really good sense of what the data structures are like. And if you're comfortable with coding in Python, and you're comfortable with NumPy arrays and matplotlib and all that, this will come very naturally to you. So it's a great place to start. And here's that. So that's pretty much that one. I think maybe I'll just, if I can take a pause here and see if there's any questions. If not, I can jump into another example, or I can go ahead and wrap up. Oh, okay, great. Yep. So I do have office hours, and I can walk you through some of those examples there if you guys are interested. But in the meantime, yeah, thanks for having me, and let me know if there's any questions.